Welcome everybody. I appreciate you coming to my session and not being enticed by the session on AI that's going on right now. It looked really interesting to me, but apparently you guys, yeah. You guys want to go with the traditional stuff. That's good. So my name's Doug LaFountain. I teach just one class here, just the rhetoric students. And so we're going to be talking about mathematics, and I kind of we'll be doing some mathematics together. That's my goal, is that as we kind of do some mathematics together, we'll kind of hopefully see sort of what I'm driving at. Before we begin, kind of piggybacking off of the previous talk, we all have a goal in mind when we're teaching math. All right, you know, you guys may have various ways of articulating that goal. My goal when I'm teaching math is, I wrote it out here, that gradually over many years, and that's important, our students will develop into accurate and independent mathematicians appropriate to their respective vocations, all right? And that vocations ties in with the mission that Mr. Spangler was talking about. That, and I don't just mean vocations as in a way of making money. They too will be parents perhaps, right? And part of your vocations as parents is doing math with your kids, right? And insofar as you do that, you are an accurate and independent mathematician, all right? Appropriate to your vocation, okay? And so I think this is good. Again, gradually over many years, our goal is that our students will develop into accurate and independent mathematicians appropriate to their respective vocations. And this is important, that it's gradually over many years. Mathematics, you know, begins right in pre-K and it'll keep on going. It'll go into the upper school. Or, you know, wherever your kids end up going to school, or whatever jobs they have down the road, there will be some aspect of mathematics. It may look different than what they started out with, but there will be some aspect of mathematics. Okay, so what is mathematics? There are various definitions out there. They're probably fine. I want to focus on a definition that I think is more accurate to actually how we work with our students and every day when we do mathematics with them. So what is mathematics? And I wrote this down. Mathematics is the habits of mind that seek to describe and to discover quantitative structure and order. All right? Habits of mind that seek to describe and discover quantitative structure and order, both for its own sake and for its applications within God's creation. All right? So mathematics does not need to always have a direct application. You know, our constant question is, you know, what am I going to use this for? You may not use this when you're an adult, all right? I am not going to promise you that. But nevertheless, mathematics is developing these habits of mind that seek to describe and discover quantitative, and that's where the numbers comes in, right? Quantitative structure and order. But it's structural, it's ordered. And but behind all this is it's not just things on the page, right? We think of mathematics as sort of things on the page, equations, this sort of thing. Mathematics is actually really going on in our minds, all right? They're habits of mind that we engage in, and the things on the page are sort of shorthand, sort of notation to convey that, all right? So I really want to focus on these habits of mind. Every discipline in this school has a particular set of habits of mind that goes with it, all right? The habits of mind that go with mathematics are going to be slightly different than the habits of mind that Mrs. Montine uses when she teaches literature in this classroom, all right? They're going to be a little bit different. But nevertheless, she's going to be teaching habits of mind. And I think that's a very good way to think about classical education as a whole. Classical education as a whole, we are seeking to develop these good habits of mind and heart as our students go forward. So let me say a little bit more of intro, and then we'll get into some mathematics. All right. How do we nurture these habits of mind? Okay. So the standard way you might think about, well, let me just ask you this. If you think about how does mathematics teaching occur, how would you describe sort of a normal mathematics lesson?
It's sequential.
It's sequential, okay, okay.
Like you can't do this until you know this.
Okay, all right, all right.
You see one, you do one, and then you teach one.
Okay. Yes, 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 yes. Yes, so the teacher typically demonstrates, right, what's a particular problem. The students then practice repeatedly that kind of problem, right? This is called mimetic teaching, all right? So we have this term for this. This is mimetic teaching. And it's basically the teacher demonstrates, and students replicate, right? Okay, and this is completely and absolutely necessary. I cannot just give my students a math problem that they have never seen anybody do before, and for them to just do it. Well, maybe some kids can, but that's just not the way it works. So mimetic teaching is absolutely necessary, and it's absolutely necessary in all kinds of skill-based disciplines. All right, we do it in science, we do it in art. If you teach an art class, the art teacher typically has to have some kind of demonstration of how am I going to actually do this technique that we're doing. We do it in music, okay? A teacher needs to demonstrate, all right, how do you play the clarinet, or how is this piece supposed to sound? And they might play it on the piano or something like this. And then, so mimetic teaching is really, it's absolutely essential, it's absolutely necessary. But what I want to argue today is that in and of itself, if we just sort of leave it just as it is, teacher demonstrates, students replicate, in and of itself, it's not sufficient. That is not sufficient for doing mathematics. Okay? So I'm going to pose that question. Why might I think that just doing mimetic teaching is not sufficient for our students to learn and do mathematics? Yeah?
Doesn't teach them to critically think.
Doesn't teach them to critically think. They're just kind of copying. They could not really understand what they're doing. Yeah?
It doesn't really teach them how to adapt and apply that concept to their life, so it's not going to really stick.
Yeah, and even more immediately, what if I give them a slightly different problem that's a little bit different than the one that I demonstrated, and then they're like, well, okay, now what do we do now, right? Something else. Why might this not be sufficient?
Because then they don't necessarily have true understanding. The whole, she said the next step would be that they teach it too. It might not be full understanding of the concept.
Right. So they may be able to mimic, they may be able to copy the procedure that you're doing, but they might not understand why the procedure works. They might not be able to teach it to somebody else. When to use it, right. And the other thing is, and when a teacher goes to grade their work, there may be a lot of thought process that's going on sort of behind their work, and the teacher is grading what's written on the page, but the teacher doesn't actually know what went on in their mind during it, okay? This is something that's difficult. So I wrote down here, students will inevitably run into problems which are not identical to ones that the teacher has demonstrated. What do they do then? Students may accurately mimic the steps that teachers are doing, but not understand what they actually are doing or why the steps work or why are they doing these steps and not others. And I can hand this out afterward. All the teacher sees to assess student understanding is the output of their thought processes and not the thought processes themselves. What I want to argue today is that we need something else, okay? And this something else is actually really easy, okay? If we just kind of remember to do it, all right? And our students get used to doing it. We need to just ask them questions along the way, okay? Asking questions, okay? Along the way. Okay, and teachers can incorporate this into their mimetic teaching. This is not something that has to be, you don't throw away mimetic teaching. You keep doing mimetic teaching, but you can start incorporating more of these good questions into mimetic teaching. And then when we as co-teachers are at home working with our kids, I got a couple kids that I work with, we can be asking them questions at home, all right? And so classically we talk about, there's a fancy name for posing questions that are sort of heading toward a goal. So questions heading toward a goal, or heading toward an objective. Classically are called Socratic discussions or Socratic questions. So if we want to think about this classically, we're just trying to incorporate a little bit more Socratic discussion into our mathematics interactions, all right, with our students. And you can do this when your students seem to be getting it, like if they're getting all the problems right, still do this, okay? And I'm talking to myself here because I get lazy, right? If I'm at home and I got all kinds of things going on while I'm co-teaching, I'm trying to grade my own papers and answer emails and stuff like this, I am not necessarily going to do this, all right? So I'm talking to myself in this talk too. But just to take a little bit of time to ask some questions. One of the things that came up in one of our teacher trainings the other day is to educate that verb. Actually, when you look back to its roots, means to draw out, all right? And these questions can draw out how the students are thinking about things. Because what they're doing is they're asking questions to themselves all the time while they're doing these problems, all right? They might not articulate them, but there's questions going on in their mind about these problems. So let's see how this works. Let's do an example. So I picked some examples. I apologize if they're not appropriate for your particular grade level, for your students, but we'll work with them. Okay, so here's an example that I grabbed from the Saxon book that my daughter worked through last year. So we want to find perimeters and areas of the following figures. Okay, so you're allowed to work with each other on these. Okay, you don't have to like, yeah. You can chat about them. Ask questions of each other, right? Do you have a little Socratic discussion? So let's see. Suppose we have this. This is my first figure. All right, and this is 5. This is 10. This is 10. This is 7. Here's my second figure. And I'm going to do some things here that, again, This is a plenary talk, so I'm trying to kind of like go, you know, through the grade levels. So I might do some things that are a little beyond, you know, your students, but hopefully we'll hit things kind of a happy medium as we go.
Are we assuming all angles that appear to be right angles are right angles?
All angles that appear to be right angles are right angles. No, this is a good clarifying question. This is excellent. That's an excellent question, Mr. Williamson. That's exactly what we want, right? Right? That's exactly what we want. Okay. All right. So take a look at those. Talk amongst each other, if you like. I don't like to talk to people when I'm doing math, so other people are different.
Yeah, that's what I got.
Oh, Mrs. Montine has pencils back there. If you want to steal a pencil.
Yeah, 40. Really, because it's fast, So this one we're divided because it's opposite sections. We're going to figure out what I'm trying to do. Yeah.
You getting graded? I have no grade books. I have nothing to record.
Does that look familiar?
Yes.
Okay, so can I use a calculator?
Oh yeah, I'll let you use a calculator.
Not in third grade.
Yeah.
Is it over book?
Is it recess time yet?
What's that?
Is it recess time?
So that,
Is it recess time? Not quite yet. No. No, they gave me an hour, so you guys are stuck here.
so square.
We're opening dialogue. So
What's that?
So I wish my kids would be math that fast.
Yeah.
exactly right. That's exactly right. Good thing I did this.
I remember doing that. It's been a long summer though. So maybe like I was doing it for my training. To calculate how much dirt I needed in Jack and just work it out just that. Whatever you say.
Well, I think about like high school now. So if you need to you know, most of the time you're not thinking about it. But that's hard sometimes. So I think you go to.
So that's a good question. Do your students use calculators?
So for certain things I allow them to use calculators. For other things I don't. Yeah. They have graphing calculators, and they're a little bit too powerful for certain things that I want them to do. I want them to, you know, not be reliant upon it.
Yeah.
But then they need them for other things. Yeah.
Yeah,
Of course, when I was doing it, they would just come out, so.
So sometimes I'll have a test and I'll have two parts, right? First part without calculator, second part with. Yeah.
I mean, just for context for the school, I think my class is the first class that they're actually told to use calculators in math, Saxon.
Yeah.
And we do it for things like compounded interest, because you're multiplying large numbers repetitively.
Yeah. So if you guys, some people are done with this, I'm going to give you a few more minutes to work, but I'm going to put up a couple problems here just for those who have finished early. Yes. So if you finished early,
Finishing early.
let's do some. We'll do some arithmetic here. Perhaps a little straightforward. More straightforward.
We're trying.
So which grade level would you start there in this second?
Well, I grabbed this from my daughter's math book. She was in Saxon 6-7 last year. Yeah. So yeah. So I like this problem. All right. So.
It's harder for me.
No. We don't. Yeah. So remember my definition of mathematics. It's habits of the mind, right? And if you stop doing those habits, you lose it. You lose it. So I do not judge people that have forgotten these things, right? All right. So this is a nice problem. Let's talk about this problem. I thought this was a pretty good problem, and it actually I had to do some kind of Socratic discussion with my daughter when she was doing it. Okay, and we'll try to guess where that came in. Okay, so let's start on the problem right here. So there are things going on in your mind when you're doing these problems. All right. And what you need to be aware of as a co-teacher is those things are going on in your students' minds too. So you need to be able to talk and discuss about these internal things. So what are some sort of observations, questions that we sort of initially think of when we look at this?
Am I going to find the perimeter of the area first?
Okay, all right. So fair enough. And did you make a decision about that?
Yeah, perimeter was usually easier.
Perimeter was usually easier, sure. All right, so we're going to think about perimeter. All right, so that's narrowing down things. All right, that's an important thing in math, right? Often in mathematics you have multiple questions. Well, let's just focus on one. All right, good. All right, so we're going to focus on perimeter. What sort of question observation then pops into your mind?
How am I going to find the missing numbers?
Yeah. There are things we don't know. All right. So what do I know and what do I don't know? All right. This is classic. What do I know for sure? What do I not know that I need to know? Right. Okay, so if your student, looks at a problem, they're like, I don't know how to do this, or I'm stuck, you know, these are some great questions to start off with. What do you know for sure about that's going on, all right? And then hopefully they'll say it. All right, in order to get the perimeter, what do you need to know? And they'll say, oh, I need to know, you know, this thing and this thing. All right, that's what we need to know. Okay, what else do we observe, or what question do we have about this?
How do you find out what the...
Yeah. How can I figure what those are? All right. And an observation might be, this shape is irregular. Okay, that's a basic observation, but that shape is irregular. It doesn't really fall into, it's not a rectangle, it's not a triangle, it's not a parallelogram, if we've talked about parallelograms. It's an irregular shape. Okay? All right. So with that in mind, what other things do we start thinking about?
Well, my brain immediately went to because he specifically asked like if all the angles looked like they were right angles were. So my brain was looking for the pattern of like, especially on that first one, like, okay, so if I shifted those lines, then it makes it a square.
Ah, that's really interesting. Okay, so you said, okay, if I scooted this one up to here, and I scooted this one over to there, that actually makes it a square. Okay, that's very good. All right. So what you're doing is you're doing some kind of rearrangement. You're looking at it in a different way. All right. So this is another good question. Can you look at it a different way to kind of illuminate something? Can we look at this a different way? Okay, great. So with that observation, did that help you figure out what the length of this side was and what the length of that side was? Yes. Why?
Because I could just do 10 minus 7.
Yeah, right. You know that this whole thing should be 10. That's 7, so this better be 3, right? And this whole thing is 10. That's 5, so this better be 5. And then you say, okay, that means that this thing over here was 5, and that this thing over here was 3. That's great. All right. Did anybody else have another way of finding that 5 and that 3?
I didn't really think about shifting the lines, but just because I'm assuming the total length, if you were to... Yes. I mean, you see this 10 over here. You kind of place that 10 over here. Yes. And you say, okay, that's 5 left over. You see this 10 over here. You place that 10 over here. There's 3 left over. Yeah.
I kind of did it that way because I saw that it would help with the area, because then if I figure the area like a square, it told me what box to remove.
Ah, okay. All right. So as everybody agreed, we can now find the perimeter, right? We can add it up. What do we get? 27 plus, let's see, it's 40, right? It's 40 because it's the same, you see?
It's also where the square.
Yeah. It's 40, okay? So that's a great example of me overthinking something, but that's all right, you know? All right, so the perimeter is 40. Okay, so let's go to the area. So you thought about the area, yeah.
How is it 40? Because a part of the shape is already cut off.
Ah. Well,
We'll go around.
The length that we have to travel is the same as if we run. So suppose I want to kind of go from here all the way back to there. The length that I need to travel on this path is the same as the length that I would travel on that path. Yeah. But your question then becomes relevant when we talk about the area, because can I just say that the area is 10 by 10? No, I can't do that. As you said, you thought about the area by taking the 10 by 10, right? You said, okay, the area is going to be the 10 by 10, which is 100. All right, I'm not using units here. We're doing unitless things. And then you subtracted from it this area, right? 15, yeah? So you get 85. Okay, there is somewhere another way that people thought about the area calculation.
I made a second, I took my line up, so I had two different squares, and I did two different areas.
Yeah. You chopped it up, right? Right? You divided it. Rectangles, right? Rectangles, yep. You divided it right there? Yeah. Or you could divide it right here. And so here you would have what? This, if you did the calculation this way, you would do your 3 times 5, which is 15, plus 7 times 10, which is 70, right? You get 85. All right. So this leads us to other questions. How can I break this problem up into simpler problems, right? We broke this irregular shape up into 2 regular shapes that we understood, all right? So how can I break my problem up into simpler problems? This is thinking mathematically. I mean, this is classic mathematical thinking. When you approach a problem and you say, okay, this is strange. I don't really know how to, I don't have an area formula for this region, but can I chop it up into something that I can work with? That's classic mathematical thinking. And that's what I'm telling you. These habits of the mind are what our students are developing, okay? And we can point them to that. All right. How about this one? How did we think about that one?
Well, perimeter is obvious because all of the sides are labeled.
You're good for perimeter, right? You just do it, right? You just add them all up. What do you get? 26, 46, 60, what is it, 61? 61. So the perimeter is 61, okay? All right, so then how do we think about the area in this one?
So I made a triangle out of,
Okay, all right. So you saw that there's a triangle kind of hanging off here, right? Right. So you divide it like that, and now you've got a triangle and a rectangle. You're happier with those shapes. They're more familiar to you. Okay, and so what do I do there?
So you have to label the other sides of the triangle.
Yes. Okay. I have this side, which is 14. So I want to find this side of the triangle and this side of the triangle. How did I do those? How did we do that?
Well, you can see the bottom is 15, and so you take the 20 from the top and subtract 15.
Yeah. So
It's hanging off the side.
right. So this is 15. So this is 15. So this is going to be 5, right? And this is going to be 12, right? But there's a bunch of questions in there, right? You know, if your student gets to there and they're like, I don't really, I don't know how to do this. You can say, okay. What's bothering you about this problem? Why don't you know how to do this? And they might say, I don't know a formula for this shape. I don't know a formula. And you can say, yeah, you're right. I don't either. We don't know a formula for this shape. But is there a way we can break it up into shapes that we understand, right? And then you start to make some progress. So all right. So this is going to be. This area is going to be 15 times 12, which I don't know off the back of my head. What's 15 20? 180? All right. So 180 plus, okay, then who remembers how to find the area of a triangle? Base times height. Yeah, this is a right triangle, right? So it's going to be 60 divided by 2, which is 30. All right. So the area is 210. Okay. Am I right?
Yes.
Okay.
Probably.
Yeah.
We thought that a squared plus b squared equals c squared, so you find the area of the triangle.
I'm going to get to that in a second. That's not area. That a there is not area. That a is referring to a length of a side. I'm going to get to that in a second.
Right. Length of the side, but that's okay.
The point here is that this is A, this is B, and this is C.
Correct. And that's how we did it.
Yeah.
And we didn't get the right answer.
Yeah.
So you would do 5 squared.
I'll tell you what. Hold that thought because I actually want to talk about this in a second. All right. I want to talk about this in a second.
What's the formula you use? Base times height.
Divided by 2 to get this.
Yeah. The area of a triangle.
Length times width is the area of
is going to be 1/2 base times height. Yeah.
That makes sense.
Yeah. All right. So I said I was doing these problems with my daughter, and
I mean, she was just working on them. And she called me in and she said, I don't know how to do this, Dad. I'm having trouble. I don't know how to do this. And so I started with this one. I said, okay, did you understand how to do that? And she explained it to me. And did you understand how to do this one? And she understood that and she explained it to me. But she said, but I'm stuck on this one. All right. And so here's where we have to have a little bit of discipline as co-teachers. And we can't just jump in and tell our students how to do something. All right. We can't do that. We need to ask guiding questions. We really need to. And so I said, all right, so how are you thinking about this? And, well, she said, she says, I just, you know, she started drawing lines. She kind of like went like that. And, you know, she kind of erased it. And then she was like, you know, she's like, oh, like that. And, you know, she was like, I don't know, like this. Okay, so I was watching her. What was my daughter doing?
Trying to figure it out on her own.
She was guessing.
No. She wasn't guessing. She was trying to do something. What was she trying to do? She was trying to divide it up into two pieces, just like she had done right here and here, right? So that was good. That was good. All right?
Not thinking outside the box.
Literally.
Right. Okay. She wasn't thinking outside the box if we use your techniques, which was to build this thing as a rectangle, and then we're going to be taking away this area, right? When we think about area. I mean, obviously the perimeter wasn't a problem here. She was fine with the perimeter. I'm talking about area. I didn't think this way, all right? I did not think of building a square, all right? Yeah. So what do you think I directed my daughter toward? I tried not to tell her the answer, but
More than a rectangle. More than straight shapes.
yeah, I said, I think you're assuming that you need to break this up into two shapes. Mm-hmm. You know, you could maybe break it up into more. And then she was like, oh, you mean like that and that? She immediately saw it, right? Yeah. So the point is that our students, when they say they don't get a problem, they don't understand it, usually there's something that they're getting hung up on. All right? Now, it's not always easy to get at that. It's not always this easy that, like, kind of as soon as I say, well, you're just thinking about, you know, breaking it up in two shapes, that she immediately sees how to do it, all right? But you can identify through questions, through having a dialogue, where she is, or your student is, and then you can do this. And so then she could figure it out from here, all right? How could you figure it out from here?
We already know what the...
You know this whole thing is 12, right? You know that this is going to be 12 times 4. So you know that has area 48, right?
You know the height of the triangle, because it's 12 minus the 4 from the rectangle.
Right. So over here I've got 12. Over here I've got 4. So I know that edge is 8. Yeah. And...
So there's another 48 in that rectangle there.
Yeah, so this is going to be 6 times 8. That's 48, right.
And so then you figure up that little piece of the...
8 times 6.
And then, yeah, so this is going to be 12 minus 6, so that's going to be 6. So this is going to be 48 divided by 2, which is 24. Yeah, you find the area of those 3 pieces, okay? But I really like your guys' observation of actually building a bigger square. This is arguably a little bit easier because now you can do the 12 times 12 is 144, and then you're subtracting the 24, right? So you get 120. Yeah. So this is a wonderful example. In mathematics, there's not one way to skin a cat, all right? You can have multiple ways of doing things that are perfectly valid. You know.
Be helpful because then you might be able to figure out an easier way to think about something.
Yes, that's right. And then you and your student, you're kind of both making a discovery, right? Like, and you know,
the same answer no matter which way we do it.
Yeah. That's super cool. And you guys just taught me something, and then you feel good about yourselves, you know. No, I'm not. That's serious. I'm serious.
I wouldn't have seen that. I wouldn't have seen to extend it into a box if whoever you were hadn't pointed that out.
Yeah. Yeah, that's right. That's right. And so this is a great example of this is a rich problem that actually has a lot going on in it. You're thinking about shapes, you're thinking about formulas, but you're thinking about decomposing. You're expanding kind of your vision about what's there and what's not there, what you can add, how you can decompose. There's so much mathematics going on. So that's what I'm saying. This is mathematics, what we are doing here. We are doing mathematics, and so so feel comfortable to do this with your children. All right. These are great examples. So let's see. I want to just read some examples of questions to ask. I can pass these out after I'm done. What exactly is confusing me about this problem? All right. This is a question that I have to ask myself. I'm a research mathematician, so I work on problems that I don't know how to do, and so that's just if you can get your students okay with that, like they're like, I don't know how to do that. Just that's okay. That's not a problem. Not a problem at all. All right. I work on problems I don't know how to do. So what exactly is confusing me about this problem? What do I know for sure in this problem? What do I need to figure out before I get to the final solution, right? Because that's part of the challenge with mathematics. Is sometimes there's multiple steps, and you kind of have to sort of tease that out. Well, what do I have to do? Have I seen a problem like this before? That helped in this example, right? The fact that we kind of went through this in progression, if we just went straight to this might have been a lot harder than if we had done this one first. Yeah?
Okay, so I know we have at least a couple of us with the younger kids.
Yeah.
How you do the guiding questions on like the very basic math?
Right.
Like we have like we're doing addition, subtraction, and we're just starting to get it a little bit more complicated where like the guiding questions are a little bit easier to find.
Yeah. Right. So I would say, one of the questions that I have here is there a way I can make a drawing of this problem? All right. That can be very helpful for kids when they're, just learning their arithmetic. So, for example, I don't know if you guys do this, but suppose I want to do 8 plus 3. All right. Okay. For a young student, that's a little bit more challenging, right? Because it's not just it's going beyond single-digit numbers into two-digit numbers, right? So what's a drawing we can do? Okay. So one of the classic ones is to have little cubes meaning one thing, right? All right, and so you start doing these cubes and you count them. You have 4, 5, 6, 7, 8. Okay, and then you those are our 8s, and now we're going to do our other number in a different color, right? 1, 2, 3. Okay? Or if you want them to start learning base 10, you stop at 10, all right, and then you do the extra 1 there. All right? That's probably more fruitful. Because now you have, this is like a 10 stack, right? And that's an extra 1. And then they can say, all right, what's 10 plus 1? That should be 11, right? So that would be an example. This kind of these drawings where you're grouping things base 10, I think, are really important for young learners. My kids started, their addition problems like this when they were like in kindergarten or when can't remember when it was. Or you can
So if you kind of develop this routine with them when they get stuck, then you can say, all right, can we draw a little cube drawing of this, all right? And they can probably, then they start to get used to this and do that. You can ask them, all right, you can try to get at what are they confused about. You could say, all right, if this was a 3, could you do that problem, right? And maybe they can do that problem. And then you kind of work it up from there, and you kind of start to see where they get confused in their addition. It might be when they go beyond 10, right? That might be the hurdle. I don't teach a lot of young kids, so I don't feel like, you know, I think some of the other elementary school teachers, the grammar school teachers, could probably have a little bit more insight here. Yeah, go ahead.
I would say the question that you ask is the same process that we went through over here. What do I know? All right, what do I not know? And so we always want to start with what we know. So for example, what does the child know at this point in time in their life? They know counting. So you start with counting. And so this is the skill that you as a teacher have to build up is, how do I know how to break this concept down into its smaller concepts? And that's something that you as a teacher have to dig into the material and learn how to do. So it's the same thing that we did over here. We took a big shape, an irregular shape, and we broke it into smaller, more manageable shapes. We took a concept over here, and we broke it from, oh no, I just broke my understanding of place value because I don't understand place value yet. All I understand is counting. And so we took counting and used that as a mode to teach them place value. And visually writing out, always a great idea.
Yeah. I mean, for me, and this is probably not something I would do with young kids, but once they start learning about a number line, all right, that's how I think about addition problems like this. I have in my mind, here's, you know, what's going on in my mind. Here's 0. I go out to 8, right? And now I'm going to go 3 more. Keep on. Ms. Montine tells me to toss these out. But and I'm going to go out 3 more, and I know I got to jump this hurdle at 10, right? And I know that hurdle is 2 away from 10, and so I know that I need to go 1 more to 11. That's going on in my head. I'm telling you, that's what's going on in my head. I don't memorize. I don't have this memorized. I sort of see it on a little number line. For me, having visuals like this is always going on in the back of my head, so we can kind of draw that out. Let's see here. We might be running out of time. So this. Yeah, so since we're kind of getting low on time, I don't want to necessarily get into other examples that I had up here that I erased. Any other questions about kind of what I'm driving at here? All right, I think the key thing for all of us, including myself, is to make sure that you take time to ask your students some questions, to try to draw out where they're confused, and then to guide them to a solution. And the point is that whole thing is doing mathematics. And that is what mathematics is. And they're asking those questions themselves. So if we can continue to do that, gradually over time, that begins to develop these good habits of mind. All right? So let me pass out this sheet here. I just wrote a few things down. I don't know if I have one for everybody. One of the things that I have down here is even if a student kind of gets it all correct, all right? My son will often get a math problem correct, but I will see no work. So I will ask him, all right, so how did you think about this? All right, and then he explains it to me. All right, that's really important, okay? Don't just accept a correct answer as, you know, I don't do this for every problem. I'll just, like, you know, sample maybe 1 or 2. But I want to make sure that
how he's thinking about it actually makes sense, and I want to hear how he's thinking about it, just for my understanding, and so I know where he's at, and it forces him to articulate. He's going to have to show work as he gets older, and so this starts to...
They actually have to show work in third grade.
Yeah.
Everybody knows.
Yeah.
Because otherwise they get a half point off.
That's right.
They could have used a calculator.
That's right. That's right. You had a question?
And label
just
it.
gonna ask, like, so we already established that I was seeing the problems and you guys were seeing the problems very differently. Would that, so the Socratic method would actually like change how you might teach something going forward? Because then the student's understanding it a little bit differently too, right?
So what I would say is this Socratic discussion in and of itself is going to be building understanding, right?
It helps you realize that maybe the way you need to teach something might be a little bit different.
Yeah. That's right. And so it's a way to actually build understanding both for the student and for the teacher, and you actually have a better understanding of where each other are at and how to help your student, and you can affirm their own discoveries, right? So that's the point, is you made some discoveries about this that I didn't see, and I can say, oh yeah, that's really great. Yeah. All right, I think we should probably stop there. I think the next session is on. So thanks everybody for attending.
Thank you.
Yep.